Claim about these sets we see epsilon, where C is a compact subset of the group gamma. So the claim that they are open, I will skip this proof as I told, because this is basically the same. Okay, and the next thing is that the sets U K epsilon form a base of neighborhoods of unity in gamma. Now, to approach to this statement, I must recall what are the open sets in gamma. I remind you that gamma is the spectrum, the Gelfand space of the algebra L1, and so its topology is induced from the conjugate space. Well, in general, if X is a Banach space, and X star is dual, then the topology, the weak topology of X star induced from X is determined by seminorms, seminorms are of the form so these are seminorms on X star. These are functions on of elements of X star, and each such function is determined by some point of X. This is what is called a determining set of seminorms. This means that, in fact, we use more seminorms to define neighborhoods. We use some maximal finite collections of such seminorms. But in any case, a neighborhood, every neighborhood of an element H in X star contains a set of the form G in X star, so that G minus H on Xi is smaller than epsilon, where I runs over some finite set. So these are basic neighborhoods of an element in the dual space. They all are defined as follows. We take some finite set of elements of X and impose such inequalities where epsilon also runs over all positive numbers. So these are basic neighborhoods of an element. Now, in my case, well, I have gamma 0 and gamma. It turns out that instead of considering all neighborhoods of this gamma 0, I must consider all the neighborhoods of this form. Consider some functions in L1 of G, and consider the set, say W, the set of all gamma, such that f hat of gamma 0 minus f hat of gamma J is strictly smaller than epsilon for all J from 1 to n. So in accordance with what I said, what I recalled about this fixed star topology, all neighborhoods of a given point gamma are defined as follows. We must fix all basic neighborhoods. We must fix some functions fj, sorry. We must fix some functions in L1, and we must consider all characters so that we have this inequality. So these are basic neighborhoods, and what we must do, we must find some neighborhood of this form in each neighborhood of this form. Given a neighborhood of this form, given a set of this form, we must find some set of this form which is included in that one. And okay, and then the claim will be proved. For any gamma naught and any functions in any functions f1 and so on, fn in L1 and any epsilon, we must find a set of this form with probably different epsilon, which is included in this.
And it has to.
Well, not quite, but we must find a set of this form such that gamma 0 plus u k delta is included in this w. Oh, you're right. You're right, because I directly started to think about this gamma 0 as about 0, which will be done in a minute, of course. Of course, we'll pass to the case where gamma 0 is 0, because everything is invariant under translation. Okay, but, well, so the base of neighborhoods of gamma 0 in that fixed star topology is defined in the following way, and given such a set, we must find another set of this form, which is included. Okay? Well, shifting everything, we may assume that gamma 0 is equal to 0. Then here we simply ensure this inclusion without gamma 0. Now what does it mean? Well, okay, here we have some functions in L1, and we know that the set of compactly supported function on G is dense in L1 of G. So this is some commonplace. You have a regular measure, so that locally compact space, so that it's dense, and this shows that we may replace these functions by functions in this set. Simply, if we approximate very tightly these functions by functions in this set, then we do a small mistake, and these inequalities persist. So we may assume are continuous and complex is imported. So this is done by approximation.
We know that it is dense in L1, but
Yes, it's dense. Well, simply take some continuous and complex supported functions which are very close to this one, and consider the same neighborhood, but defined in the same way, but with those approximants, probably with small epsilon. Then, if we have this estimate with those approximants, probably with small epsilon, and maybe even not, because we have strict inequality here. Again, we use the fact that the spectral norm is dominated by the L1 number. So simply the spectral norm is dominated by the L1 norm, so we use again this fact, and then we may replace them by everything which is close to them, and it suffices. So let's assume they are complex supported and continuous. And let K be the union of their supports. The union of closed supports of the Fj, and this is a compact set. So we shall take this compact set as this K, and for this number delta, we take something very, very small. We gamma 0 is equal to 0 right now. This is equal to 0, okay, this is equal to 0, and we have, suppose we have an equality of this sort with something small. Then we must ensure something like that. So f hat of 0 minus fj hat, fj hat of gamma. What is that? This is the integral over g of f of x 1 minus gamma of x bar dx. And in fact, the integral is over k because all functions are supported on k, fj. And this is less than or equal to, well, if I take the absolute values, this is less than or equal to. Here, this is at most delta. The integral over k of the absolute value of j. So this is delta, the norm of fj in L1 of g. Yes? And now we see that if delta is very small, then we can ensure that this thing is smaller than epsilon. And since the number of the functions is finite, then everything goes smoothly up to the end, okay? So that's quite easy. Well, now we have this base of convenient neighborhoods of unity.
Where did you use the continuity of fj?
Nowhere. Simply, I needed that they be completely supported. But as to continuity, well, yes.
Supported L1 functions.
Yes, but how do you know that completely supported L1 functions are dense? Probably the shortest way to show this is precisely to use the fact that continuous completely supported functions are dense. And this is a commonplace from the regularity of measure. When you construct your measure by the Ries theorem, then this emerges immediately, and so somehow. But as long as you know that your measure is regular, then of course this is easy. So this way or another, well. No, at this point, no use of continuity. Well, okay. And now, the last thing is the mapping this mapping is continuous. From gamma cross gamma to gamma. This will finish the proof of the fact that gamma is a topological group. So, well, okay. So, a basic neighborhood of gamma 1 minus gamma 2 is a set of the form of this form. So I must find some basic neighborhoods of these 2 points, so that their difference belong to this one. Well, take gamma 1 plus u k epsilon over 2 and gamma 2 minus u k epsilon over 2. Well, by the way, here whether you put plus or minus is the same. Because this neighborhood U is determined by the following inequality. Gamma of x minus 1 is less than epsilon for x and k. And what happens when we put minus here? When we put minus here, we should put bar here over the gamma. Yes? We should put bar here. And so this inequality is stable under complex conjugation. So, so it's the same. Plus or minus is the same. They are symmetric. Simply these neighborhoods are symmetric. And this is natural because in any group there should be a base of symmetric neighborhoods. So these neighborhoods are symmetric at once. So if delta belongs to u k epsilon delta 1 over 2 and delta 2 belongs to u k epsilon over 2, then what do we have? This means that and after that, if we take the difference, and what the difference is delta 1, delta 2 bar of x, and we must estimate this thing. And this is less than or equal to this is simply equal to delta 1 of x minus delta 2 of x, surely, because I multiply by some complex number which is equal to 1 in modulus, and this is less than or equal to delta 1 of x minus 1 plus delta 2 of x minus 1, as this is smaller than epsilon. So this means that really the sum of these two neighborhoods, is included in this one. The difference of these two neighborhoods is included in this one. And so this is really a topological group. Now we have recognized at least a part of symmetry between these two objects, G and gamma. At least we know that gamma is a topological group itself, and it is locally compact. Well, but still we don't know how large it is. Maybe there are very few characters only. Okay. Well, now I recalled what I forgot when I listed properties of the Fourier transform, elementary properties of the Fourier transform. And this is also quite elementary. Well, the following thing, that if we take the convolution of two functions and take their Fourier transform, then this is the multiplication of the Fourier transforms of f1 and f2, the product. Well, and this is again, it can be proved by integration. So if we integrate this with some characters, then it is easy to obtain that. But in fact, this is not required, because this is again a consequence of the Gelfand theory. This thing, the mapping which takes any function to its Fourier transform, this simply is a Gelfand transformation. So it takes product in the initial algebra to the product in the algebra of the images. So that's precisely what we see here. But in any case, if we only know what a character is, and if you write what this means, then we easily see by changing the order for integration. But by transforming some integral, that this is what we expect. Okay, so we have this equality, which is trivial in our setting, and to go further, we need the Fourier transform for measures. What is that? Now, in this setting, by a measure, I mean a finite regular Borel measure on a group. So the Haar measure, which is maybe infinite, may fall out this context. So we have the Haar measure, which is probably infinite, probably not. But now, when we convolve, we consider only finite measures. And the convolution of two measures, the easiest way to define it is as follows. Consider the space C0 of gamma, of G, of G. The set, okay, not C0 probably, no, not C0. Or C0, maybe even for simplicity, even let's consider the set of all compactly supported continuous functions on G. And consider two finite regular on G. Then consider the following functional phi it is defined as the following way. So this is well-defined linear functional, and moreover, the Riesz representation theorem applies to in the setting. Well, when I, as the first lecture, formulated the Riesz representation theorem, I we restricted ourselves to positive functionals, and here, in principle, we may reduce the situation to positive functional because every finite regular barrel measure is a difference of two positive measures. Well, if it is complex, in principle they are complex, but then they are represented in terms of some linear combinations of four positive measures. And so by linearity we can reduce this definition to positive measures only. And if mu and nu are positive, then this formula defines a positive functional on the space, a positive functional on the space, and this functional is generated by some measure, of course, by the Riesz theorem. And this measure will be finite because, well, for clear reasons, this will be finite because these are finite. Well, so this is, in any case, not matter whether they are positive or not, this is generated by some measure lambda, which is also regular barrel and finite, and so we have this equality. Thus lambda is defined uniquely by mu and nu, and this lambda is called the convolution. Of mu and nu, and the notation is as usual. Well, from this definition, it is clear that convolution is a commutative operation because of the Fubini theorem. I don't know. Well, it is also easily proved that it is associative. If you convolve more than two measures, then the way of posing the parenthesis is not essential, because in any case, this will be the integral of f of the sum of some arguments against these measures, each one in its own argument, and so on. Well, and also here I must tell you that I skip some easy but a bit nasty measurability questions. Well, because if we discuss them, well, it will be very dull and not interesting. Anyway, the first thing is that this formula passes to bounded measurable functions, at least Borel functions. Well, you may replace here f by any Borel function.
You mean replace e mu by f e x?
Yes, I may place here a Borel function f.
Yes. Is it the extension of our original definition?
Yes, it's general, but okay. So you may place here any Borel function f, which is measurable and bounded, of course, bounded. For example, you may place here the characteristic function of a set. E is a Borel set in G. So from this we obtain that lambda of E, we find this here, is equal to integral over G, the integral over G, he E of x plus y d mu of x d mu of y. Okay? And if we integrate here first in the measure mu, then what is this? This is the characteristic function of which set. So for this to be equal to 1, we need that x plus y belong to E. So this is equivalent to x belongs to E minus y. So this is equal to integral over G of the measure of E minus y okay. We may write this in this way. And this, of course, resembles very much the formula for the convolution of functions. There also we consider the shift of a function by minus y, and then so here we consider the shift of the measure by minus y, and then integrate this against another measure. And when we consider the convolution of two functions, we shift one function by minus y, and then integrate this by against another function. So, well, okay. And precisely when we manipulate this way, some tiny measurability problems arise. So we must here to be able to use somehow the Fubini theorem. And when you think why it is possible, well, you quite soon you find that yes, this is really possible. But before you find this, you should think a little. In any case. Okay. So from this formula, it follows that if mu is absolutely continuous, with respect to the Haar measure, then so is the convolution. Well, if mu is absolutely continuous with respect to the Haar measure, then it is equal to 0 on each set of Haar measure 0. So take for E a set of Haar measure 0. Then the shift by y of this set also has Haar measure 0. Since mu is absolutely continuous, this is also 0. Then this is 0. So the convolution is 0 on each set of Haar measure 0. So it is absolutely continuous. Next, it's precisely time for the break. No, not quite. Not quite. We have still some 12 minutes before the break, okay. Next, mu is absolutely continuous. Then it has a density. has a density. Well, and let's write this integral in the case mu has a density. Lambda of E is equal to, well, what? Sorry?
What is it?
Not minus lambda, but minus y. Minus y. Okay?
There is one more integral.
Sorry?
There is one more integral there.
Yes, there should be one more integral. And here also we should have one more integral. I change the order freely, forgetting about all measurability. Sorry? F is the density. F is the density. F is the density. So this way we see that the density of lambda is equal to this integral. So this is the density of lambda, this way. And the next step, suppose that nu is also absolutely continuous. Is density G. Then the density of lambda is equal to what? G, small g, of course. This integral over nu will be simply integral with the function g over the higher measure of g. Yes? What happens if we convolve two absolutely continuous measures? Then the density of this convolution is obtained as the convolution of the densities of these measures. Next, with this play of density and so on, we may assume that L1 of G is embedded in the space of measures. Let us define the space, denote the space of measures on G by this symbol, M. M is the space of measures with the usual total variation norm and so on. Now L1 is embedded here simply to each function. In L1 we assign the measure whose density is equal to this function.
You've already used L of something as
Okay. Well, okay. How to how to define the space of measures? How to know the space of measures?
Well, you could see beautiful.
Okay. Calligraphic. Yes. Sure. Okay. So let this denote the space of measures. Then we have an isometric embedding. And what do we know? We know that this space of measures is an algebra under convolution also. We know that this thing is a subalgebra of this algebra. Yes? If you convolve two absolutely continuous measures, we obtain an absolutely continuous measure whose convolution, whose density is a convolution of the densities. Yes? Also, moreover, this is an ideal here, because if we convolve any absolutely continuous measure with any other measure, we obtain an absolutely continuous measure. Yes, this is an ideal. Now, what else? What else? We have this inequality. The easiest way to use this is to view this is the functional on the space of continuous functions. If we write this formula, we immediately see that a crude estimate of the right-hand side yields this norm estimate. So this is dominated by the uniform norm of f times the product of total variations of these measures. So we have this. Next, the algebra M of G has a unity. Is a unity, and this is the delta measure at 0. Should I explain why this is a unity? Well, again, if you write this formula and one of them is a delta measure at 0, we see that everything reduces to the other measure. So this is an algebra with unities. This guy is an ideal in this algebra. Also, when we talk about absolutely continuous and singular measures, we may revoke what is called Lebesgue decomposition. And Lebesgue decomposition tells something more substantial, that if you have a measure, it decomposes in three parts. One of them is absolutely continuous with respect to the Haar measure. The other of them is continuous, that is, it is singular but has no point masses. Continuous singular, and the last summand is discrete, that is a countable combination of point masses. And what's about this? Suppose mu is continuous. Suppose mu is continuous, what's about the convolution? Well, again, look at this formula. And what does it mean that mu is continuous? It means that it is equal to 0 on every countable set. It has no point masses. Yes? It has no point masses. So suppose E is a countable set and mu is continuous. Then this shift is also countable. So this thing is equal to 0. That is, the convolution is also equal to 0 on every set, on every countable set. This means that convolution also doesn't have point masses. And so the set of continuous measures is a subalgebra and even an ideal in the algebra M. Okay? And as to discrete measures, it is clear that this is subalgebra. If you convolve two discrete measures, you obtain a discrete measure, and this is just visible because if you convolve two point masses, you obtain a point mass as the sum of the points where they are supported. So this is some structure in this algebra related to various properties of continuity and absolute continuity, discreteness, and okay. Okay, but what is interesting is that we can extend the Fourier transform to this algebra. Sorry? Yes, sir. Uh-huh. So let mu be in this algebra. Then and let gamma be in gamma. Then mu hat of gamma, by definition, is equal to the integral over g of gamma bar of x dmu of x. So again, if mu is absolutely continuous, we obtain simply the Fourier transform of this density of the measure mu. If mu is absolutely continuous with density S, then we obtain the Fourier transform of this density. So this formula simply extends the Fourier transform from L1 to this algebra of measures. And what else? Here again, the Fourier transform of a convolution is equal to the product of Fourier transforms. And when we dealt with functions, we said that, okay, this is easy, but no proof is needed because it's the consequence of the Gelfand theory. Now it is not a consequence of the Gelfand theory, but the proof is easy from this formula. If you substitute a character for f here, a character with bar for f here, then you see that everything splits. So we have this. Now we have a break.
Can you say something about the growth of space of MG?
Maybe we'll study this. Of course, the Gelfand theory applies, and there is some space. It is much wider than the space gamma.
Yes.
And even there is a thing which is called Wiener-Piet phenomenon, which says that the Fourier transform of a measure may be separated away from zero without this measure being invertible in this algebra. Well, if so, there is the so-called Tauberen theorem of Wiener, which says that if you have a function L1 and its Fourier transform is separated away from zero, well, this applies only to compact groups, of course. There should be a unit. Then this function is invertible in the convolution algebra. This is a consequence of Gelfand theory again, but here, if the Fourier transform of a measure is separated away from zero, it is not necessarily invertible. So there may be much more various multiplicative functionals on this algebra, except the characters, and they are non-visible and they are very complicated and all transfinite and so on. What should I say next? Well, algebraic properties probably I mentioned. Well, later, I don't know, maybe the next time, maybe in 2 weeks, we shall prove the following uniqueness theorem. If mu is a measure on G and mu hat of gamma is equal to 0 for all characters gamma, then mu is equal to 0. This is not easy, and this will be postponed. So in particular, this means that there are fairly many characters on G, because there are sufficiently many characters to distinguish measures. And right now we don't know if there are many characters. So right now it is not accessible to us. But what is accessible is the dual statement, a counterpart of this for the group gamma. So suppose mu is a regular barrel measure on gamma, and suppose that the following integral over gamma is 0 for every x, for every x in the group G. So, as you guess, all characters on gamma will be of this form. So we already discussed that the situation is symmetric. So later we'll see that all characters of gamma are of this form. So this is a general form of a character on gamma, and so this is the Fourier transform of nu as a measure of gamma. But we don't know this for the moment, because we don't know what the dual group of gamma is. We don't know whether it is G or something else or something smaller, I don't know. But still we can define such a function on G, and suppose it has to know that it's equal to 0 identically. Then nu is a 0 measure. So I cannot prove for the moment this statement, but I can prove this counterpart of the statement for the dual group. After we will see that it also extends to the original group, but not quite immediately. Well, to prove this, we simply do the following. We take a function f in L1 of g, L1 of g, and integrate this with f. Well, consider the integral consider this following integral. So this is a double integral. We integrate over gamma and then over g in x. And of course, this is equal to 0. But then we change the order of integration. And what do we obtain? When we change the order of integration, we first integrate here in x. And we obtain simply the value of the Fourier transform of f at the point gamma. So f hat of gamma d nu of gamma. So this integral is equal to 0 for every function f in L1. But the Fourier transforms of the functions f in L1 form a dense subset of the set C0 of gamma. So this means that the measure nu generates a zero functional on this space, and consequently it is equal to 0. Okay? So in this direction, this is easy. We mentioned this at the very beginning.
Yeah, I mentioned what is the, how do you use it?
Well, the functional generated by mu is equal to 0 on this set.
Yes.
But it's continuous here. So, and this is dense here. So it is 0 here. And if a measure generates a 0 functional on this space, so the space of measures is the dual of this space. Well, this is locally compact, the conjugate, Riss theorem, Riss representation theorem. So
it's about functionals and the measures.
Yes, functionals, and vice versa. Here, the difference is that here we consider the set of functions that tend to 0 at infinity. Yes, but if we consider the one-point computation of this space gamma, then the usual Riss theorem is applicable. When we pass back to this subspace, we see that its dual is a set of measures on this one-point computation which do not have a point mass at this point at infinity. So simply, this is a set of measures on gamma, regular Borel measures, and since it is 0 on dense subset, it is 0, and so the measure is 0. So everything via this representation theorem, starting with the Haar measure and so forth. Okay. And also there are some quite easy and routine facts which are proved in the same way as the corresponding facts for L1. The set of Fourier transforms of measures is translation invariant. and it is stable under multiplication by the functions of the form gamma of x. They are viewed as functions of gamma, of course. So take point x of g, and then this is a function of gamma. And this is precisely the same calculation as it was for functions. So just consider a shift of a measure, then we obtain, then the Fourier transform will be multiplied by some character, and consider the multiplication of a measure by some character, then the Fourier transform will be shifted. So I don't repeat those calculations, this is the same. Okay. Now, to prove some inversion formula for Fourier transforms of general measures, we need what is called the Bochner theorem. And the Bochner theorem simply describes inversion formula for Fourier transforms of some functions in L1. Well, we need the Bochner theorem, and the Bochner theorem describes describes the so-called positive definite functions. So the definition is as follows. A complex function on G is said to be positive definite if we have the following inequality. So here the sum may be arbitrarily long. It is a finite sum, but the number of summits is not restricted. So the condition is as follows. Take some capital N points in G, where capital N is arbitrary, and take some capital N complex numbers. Then we should have this inequality. I immediately state the Bochner theorem. It turns out that such functions are related to Fourier transform of measures on the dual group. So Bochner's theorem a function phi on G is positive definite if and only if there exists a measure in M of gamma. These are regular barrel measures on the dual group that is non-negative. And phi is represented in the following form. Well, this is near the Fourier transform of a measure, but I don't put bar here. This doesn't matter very much. Simply, it is more convenient in this setting not to put bar on the character. Again, if we knew that G is the dual group of gamma, if we knew that all characters of gamma are precisely the points of G, then this will be near the Fourier transform of mu. Right now we don't know what's about the relationship of G and gamma, but still we can write this formula, and this is very similar to the definition of the Fourier transform on the group G, so something like the Fourier transform of gamma. And it turns out that this is precisely the form of all positive definite functions on our initial group. So probably there is no shorter way to prove the inversion formula for Fourier transforms than to use this Bochner's theorem. So this will be employed to prove the inversion formula for Fourier transforms, and after this everything we claim it about the relationship between G and gamma will become clear very soon. But to prove this inversion formula, this Bochner's theorem seems to be unavoidable in this general setting.
Do we need some continuity?
It is continuous automatically.
Yes.
Phi is continuous.
In some cases, we state continuity.
It is continuous automatically. Well, we'll see this. We'll see why. I'll explain some. So here. Well, here the continuity is complex continuous. Yes, sure. Okay, that's true. Yes. This is required, of course. This is required. Now, we can prove this theorem in one direction, at least. So if we write here if and only if, then this will be the proof of the if part. This will be the proof of the if part. The fact that this is continuous in x is quite easy because this is a continuous function when we integrate simply limit passage under the integral sign follows from the Lebesgue dominated convergence theory because these functions are dominated by 1. So this is continuous, and let's verify this inequality. So the sum I start with 1. And so we need to estimate the integrand simply. Mu is a positive measure, so we should prove that the integrand is positive. And as to the integrand, so that would be I. I is equal to the sum this is the following sum, and surely this is none other than the sum over j from 1 to n, cj gamma of xj squared. Okay? When we write this square as the product of this thing times the complex conjugate of this thing, and then we make all multiplications, and we obtain precisely, when we expand, when we obtain precisely this sum. Sure. So this is non-negative, and thus this thing is non-negative. Suppose I referred to the dominating convergence theorem, but this is applicable only in the case when our group is metrizable. But right now it is not needed, because we have proved that this function as a function of two variables is continuous on the product of gamma and g. So if x is close to x prime, then this thing is close to, okay. Yes, this is this gamma is also absolutely uniformly continuous, and this was this can be proved by the same trick as we did in the proof of the continuity of this function in two variables. So simply we should represent it in terms of the Fourier transform of a shift of some function f. And then, yes. And from that formula, it follows that it is uniformly continuous in X. Huh? So, okay. An important point when we prove the inversion formula is that there are some other functions which are on the group G, which do not depend on this representation. Well, of course, when we take from mu a delta measure, then we see that all characters are positive definite, and simply we used the fact that all characters are positive definite in this proof. Here we simply showed that when we integrate some positive definite functions against a measure, we obtain a positive definite function. But the point is that except characters, there are other functions which are also easily seen to be positive definite. And what will be quite useful when we shall prove the inversion formula is the following example. which is irrelevant to characters. What is interesting here is that it's irrelevant to characters and to this representation. It is independent of all that. So example, but this example will be very important for what follows. Again, for f, we define f tilde as f of minus x bar. So this thing. Now, example is as follows. If f is an L2 of g, if it is a square integrable function, then f star f tilde is positive definite. We saw last time that this function is continuous. You remember when we convolve some function in LP and with some other function in LP prime, then we obtain a continuous function. And here it is precisely this case. So L2 is dual to L2, so we convolve two L2 functions. So we obtain a bounded continuous function, and so let's denote it phi. Then the sum of Cn Cm phi of xn minus xm. This sum is finite. Simply, I don't write the limits. Sum finite sum. Sorry.
Cn bar.
Cn bar. Yes, sure. Complex conjugate. Okay, so we write what the convolution is, and if we take into account all these transformations, we see that we obtain the following. Okay. Okay. After that, we simply change the variable here so that to split this xn and xm between these two factors. So by the invariance of the Hauer measure, this is equal to the sum of Cn bar, integral over g f of xn minus y, f of xn m minus y bar dy, and again we obtain here some square of the modulus of a complex number. Again, when we expand the sum trivially, then we obtain this. Yes? And this is non-negative. This is non-negative. Okay. Okay. Well, as I told, this is some independent example of a positive rational function, and in particular, if we know the Blochner theorem, we know also that this function phi, this function phi, is represented as an integral over some measure on the dual group, and this will be very useful in the sequel. Very useful. So I still have some time, but probably it's reasonable to stop here, because otherwise I should start something quite new and stop immediately after the beginning. Okay.
Maybe I missed something, but did you prove the only if part?
No, this is difficult.
Will we do it?
Yes, sure, we will do this, but it is not immediate. It is probably the most decisive step of entire theory.